Hi there, Mr. Sutton here, bringing you the AB Calculus 515 Extra Practice Number 2 solutions on integration by substitution of definite integrals. Trying to evaluate this definite integral, I happen to notice that we have an inner function whose derivative is elsewhere in the problem. So one way to do this would be integration by substitution. Now we could also actually expand this and multiply it by 6x. So probably half a dozen of one, 6 of the other, but I'm going to go the substitution route on this one. So we can say u equals x squared minus 1. So then du, the derivative of this is going to be 2x dx. And then dividing by 2x to get dx by itself. Now we also have to convert these x values in the limits of integration to u values. So if x equals -1, that's our lower limit right now, then plugging that into u, that's going to be 1 minus 1, that's going to be 0 for the u value there. And if x equals 2, plugging that in, that's going to be 4 minus 1, which is 3. All right, converting everything now. For our limits of integration, we're going from 0 to 3. And now we have 6x times u squared. And instead of dx, we have du over 2x. Simplifying this a little bit, the x's cancel. The 6 over the 2 gives us a 3, so we have 3u squared du, evaluated from 0 to 3. And now we can use the reverse power rule on this one. This will bump up to an exponent of 3. Dividing by that, we just have u to the third, evaluated from 0 to 3. So that's going to be 3 squared minus 0, or 3 cubed minus 0 cubed. So that ends up being 27 minus 0, or just simply 27. On this problem, since we have an inner function that's linear, one way you could deal with this problem would just be to take the antiderivative of the outside. So right now you have 5x minus 1 to the 1/2 power, so the antiderivative of that, and then just divide by the derivative of the inner function, divide by 5. And that's certainly one way to handle this. Another way you could handle this, though, now that you know substitution, would be to use u substitution. Let's let u equal 5x minus 1, so I'll just show you this way of doing it. And then du is going to be 5 dx. So then we can say du over 5 equals dx. Now let's convert these x values to u values. If x equals 2, then 5 times 2 minus 1 is going to give me 9 for the u value. And if x equals 10, 5 times 10 minus 1 gives me 49. So plugging all that in, we can write this as the integral from 9 to 49 of the square root of u du over 5. Okay, so let's see here. This is really u to the 1/2 power, and we'll have a 1/5 out in front of that. Using my reverse power rule, this bumps up to a 3/2. Multiplying by 2/3, we've got a 2 over 15 out in front, u to the 3/2 from 9 to 49. And then let me yank this 2/15 outside. And inside now I'm going to have the square root of stuff cubed. So we're going to have the square root of 9 cubed, or 49 cubed, minus the square root of 9, and then cube that. So this is going to be, let's see here, square root of 49 is 7. Cubing that, I happen to know, gives me 343, but you could certainly multiply it out by hand. And then over here, square root of 9 is 3. Cubing that is 27. If I subtract these, that's going to give me, well, let's see here, 316, and 2 times 316, that's going to be 632 over 15. Now, since I'm already kind of on a simplifying kick here, can I go any further? Well, the only things that 15 is divisible by are 5 and 3. Clearly, 632 is not divisible by 5. How about 3? Well, let's see here. 6 plus 3 plus 2, those digits do not add up to something that's divisible by 3. So we can't divide any of this by 3. This is as good as it's going to get. For this one, I want the definite integral of x minus 2 to the 20th from 0 to 2. Now, since this is an inner linear function, you certainly could do this by just taking the antiderivative of the outer function. So you'd have, let's see, this bumps up to a 21. Dividing by that, we have 1 over 21 times x minus 2 to the 21st. And then you would just divide by the derivative of the linear inner function, which is just 1. So you really wouldn't have to do any extra work. And that would work out just fine. But I am going to show you the technique of u substitution here, because that also is another way to do this problem. So let's say we let u equal x minus 2. And then du is going to be 1 dx, which means that dx and du are really the same thing. If I have a u value, or an x value rather, of 0, that means I have a u value of 0 minus 2, so negative 2. And if I have an x value of 2, then I have a u value of 2 minus 2, which is 0. So plugging all that back in, we have the integral from 0 to negative 2. Actually, from negative 2 to 0, that's the direction. Negative 2 to 0. And then we're going to have u to the 20th. And then this is just going to be a du instead of a dx. So antiderivative, this is going to be 1 over 21 u to the 21st, evaluated from negative 2 to 0. I can pull out that 1 over 21. And in here, I've still got 0 to the 21st minus negative 2 to the 21st. So 0 is obviously going to just give you 0. Here we have an even number of negatives if you count 21 negatives over here. So that's going to give you a positive. We're going to have positive 2 to the 21st over 21, which I'm not going to bother simplifying further. We're just going to call it a day on this one. For this problem, they want us to rewrite but not evaluate this integral in terms of u. So we have to figure out a good inner function on this one, and probably this interlinear function of 1 plus 2x would be a good place to start. So let's let u equal that. And then taking the derivative of both sides, we have du equals 2 dx. So then du over 2 is the same as dx. We also have to convert these x values for our limits of integration to u values. So if x is 0, then u is going to be 1 plus 2 times 0, so 1 plus 0, or just 1. And if x is 13, now we have u equaling 1 plus 2 times 13, or 27. Plugging all this back in, we've got the integral from 1 to 27, and now we have dx over, this is going to be the cube root of u squared. And don't forget, instead of dx, we now have du over 2. So we'll put that over here, actually, right next to it. Simplifying this a little bit, we can write this as, let's see, a 1/2, and I can write this as u to the negative 2/3, integrated from 1 to 27, and that'll do it. For this problem, they want us to write but not evaluate this integral in terms of u. Now this definitely looks like a good candidate for u substitution because I have this inner function of 4x squared plus 2 whose derivative is elsewhere in the problem, something with an x in it. So let me start by letting 4x squared plus 2 be my u. And then I can say du equals 8x dx. And then that means dx is really du over 8x. Now we have to convert these limits of integration to u values because right now they're x values, which we can tell because it says dx. So if x is 0, then u is going to be 4 times 0 squared plus 2, or just 2. And if x is 1, well, now we have 4 times 1 squared plus 2, which is 6. All right, substituting back in, we have the integral from 2 to 6 of, now we have negative 8x over u squared. And then we also have, instead of dx, we have du over 8x. Canceling out those 8x's and cleaning things up a little bit, I can write this as negative integral from 2 to 6 of, let's see here, we have u to the negative 2 power du. And that's as far as we need to go. They said we do not have to evaluate. For this one, we want to rewrite this in terms of u, but we don't have to evaluate it. So in order to do this, I have to spot an inner function whose derivative is elsewhere in the problem. Well, cosine is an inner function. It's inside a squaring function, and the derivative of cosine involves a sine. So let's let u equal cosine and go from there. So if u is cosine, then that means du is going to be negative sine of x dx. So then I can write du over negative sine of x equals dx. I'll also need to swap out these x values in my limits of integration. So if x is 0, then u is going to be the cosine of 0, which is 1. And if x is pi over 3, then u is the cosine of pi over 3, which we know to be 1/2. So I have the integral from 1 to 1/2 of, now I have sine of x over u squared, and instead of dx, I have du over negative sine of x. Sine and this sign down here are going to cancel. So if I clean this up a little bit, I can write negative integral from 1 to 1/2 of u to the negative 2 power du. On this problem, they want the integral from 0 to pi of this craziness. So this is one of those where it'd be nice if you could simplify the fraction, but we really can't. But one thing I do notice, if we think of this denominator as kind of an inner function here, we have a function inside this denominator whose derivative, e to the x minus x, the derivative of that is actually e to the x minus 1. So that being the case, I'm thinking some u substitution might help me out here. So let me set e to the x minus x equal to u, and then I can say du equals e to the x minus 1 and all of that with a parentheses and a dx. And then if I divide by e to the x minus 1, I've got dx by itself. Now I also have to take into account the limits of integration, which right now are both x values. So I have to convert that to u values if I want to follow through on all this. So if x is 0, then u is going to be e to the 0 minus 0, which just comes out to 1 when all is said and done. And if x is pi, well, now we have e to the pi minus pi, which isn't very nice to look at, but I guess it goes with the territory here. So rewriting this integral now, in terms of u, we can write this as the integral from 1 to e to the pi minus pi. And then we have, let's see, e to the x minus 1 over just u. So that's not so bad. And then instead of dx, we have du over e to the x minus 1. Now, conveniently, these e to the x minus 1s cancel out completely. And I've just got really 1 over u, or u to the negative 1 at this point, if I clean that up a little bit. Antiderivative of 1 over u, that's going to be ln of absolute value of u. So we'll evaluate that from 1 to e to the pi minus pi. So plugging in some things here, we have ln of e to the pi minus pi inside an absolute value. And let's see here. You actually don't need the absolute value because that is a positive number. Then we'll also subtract ln of 1. However, I mean, you might be noticing you don't see this in the answer choices. The thing is, ln of 1 is just 0. So this really is just ln of e to the pi minus pi. And that is going to be answer choice D. This problem right here is kind of interesting. So we have some selected values of a twice differentiable function g in this table up here. And they want the value of this integral. Now the interesting part about this is a calculator question on which they're just asking for the value of an integral. So theoretically, you should be able to just plug this in your calculator and call it a day. But you can't quite do that because this g function, we don't really know what it is algebraically. I mean, we've got this table of values, but that's obviously not the whole picture. So we have to kind of sort of do this by hand for a while until we can get in a position where we can use the calculator and get one of these crazy answers. So how could we figure out the antiderivative for this? Well, one thing to notice here is that we have an inner function. And not only that, but we have an inner function whose derivative, which involves a g prime, is elsewhere in the problem. So substitution is a good one to try on this one. Let me start by letting u equal 2g of x plus 1. So then I can write du equals 2g prime of x dx. And then du over 2g prime is going to be the same as dx. We also have to convert these x values into u values. So if x is 0, then what's u going to be? Well, that's going to be 2 times g of 0 plus 1. Well, g of 0 right here is 5, so this is really 2 times 5 plus 1, which is going to be 11. And now if x is, let's see here, if x is 3, then u is going to be 2 times g of 3 plus 1. Well, what's g of 3? It's negative 2, so we have 2 times negative 2 plus 1. That's going to come out to negative 3. So now I have the integral. I can rewrite this as the integral from 11 to negative 3, which is kind of interesting, of g prime of x cosine squared of u dx. But instead of dx, I want to write du over 2g prime of x, because I don't want to have any x's left if I can help it. And the other nice thing about changing dx to this stuff here is these g primes are now going to cancel out, which is great because we know absolutely nothing about g prime. We only know a little bit about g. G prime, we've got zilch. So this ends up being 1/2 cosine squared of u du. And at this point, since this is a calculator problem and I know exactly what I'm doing algebraically here, I am just going to plug this in the calculator. So just to make things a little bit cleaner, I'm going to enter cosine squared of x as my y1. And then let me quit out of there. And I'll do, let's see, fancy fraction 1/2. And I guess I didn't need the 1/2 outside the integral, but it looks kind of nicer. So we're going to multiply that times, let's see here, math 9. So integral from 11 to -3. Make sure you write these in the correct place. It's opposite from what it looks like it ought to be. And then we do alpha trace y1, and then a dx. Enter. And that comes out to approximately -3.464, which gives us answer choice B.